So a little bit about who I am. My name's Alex Theedom. I'm from the UK, and I work as a senior Java developer. I have a blog on which, from time to time, I publish articles, some more interesting than others, but by all means, have a look. And if you want, you can contact me via Twitter. Okay. I really do want to hear from you. I want to hear what you have to say and any comments that you have. Okay. I like to interact with people as much as possible. And often I go to conferences and I talk about various different topics. Today I'm talking about servlets and HTTP2. This is a new topic for me, so this is very interesting. I really am right behind the servlet development that is going on at the moment, and certainly the adoption of HTTP2. And we'll be talking about that for the next 50 minutes or so. Okay, so this is what we're going to be talking about. So here's how I'm going to spend the next 45, 50 minutes of your valuable time. So first of all, I would like to establish the reasons why we need HTTP2. Okay, then I'll look at some of the workarounds that are used to overcome the shortcomings that currently exist in HTTP1. I'll then focus on the contrasting ways that HTTP1 and HTTP2 perceive the use of sockets. And we'll talk a little bit about what the specification says and what current practices are. Then I'll look at the top-line features of HTTP2. This is a fairly meaty section. There's quite a lot of technical detail here, and I think this is particularly an interesting part, as this really underlines many of the changes that are in HTTP2. And then I'll see how those changes manifest themselves in Servlets 4, with plenty of code examples. There's some interesting things to say about the current development of Servlets 4 and various server implementations. So I'll have a quick look at the current state of server support, which servers support servlets, and who's doing what in the space. Then I'll have a quick mention of SPDY and what's happening with SPDY. And then I'll have a look at some tools that demonstrate how performant HTTP2 really is. Some providers have given us some very interesting online tools that allow us to demonstrate or test how HTTP actually really performs compared with HTTP1. Then I'll talk about how HTTP is being adopted. I'll examine some stats, look at who's adopting HTTP, how is it being adopted, and how far we have yet to go before we are 100% HTTP2. And then I will finish with a roundup of how you can get involved with the development of servlets and some questions and answers. Okay. So, what is the goal of HTTP2? Well, the overriding objective is to increase the perceived performance of the web browsing experience. And why do we need this? Well, the way in which web pages have grown and developed over the last 21 years is remarkable. Web pages download more resources now compared to 21 years ago when the HTTP protocol was standardized. A typical page back then was just a simple HTML page with a few images, and less than 1K in size. The protocol was designed, HTTP1 was designed to serve this kind of content. A small page with a few images, a few CSS, and some JavaScript. But let's fast forward to 2016, and the average web page looks completely different. Sorry. This is what what I wanted to say is this is what a page looks like in 1994. Okay, this is the BBC website in 1994. And as you can see, it's a very, very simplistic site. Sorry, I'm having problems with my very simplistic site. And this is what it looks like now. This is what it looked like yesterday. As you can see, you've got the latest news on the top there, and it's full of images. It's full of dynamic content. It's full of interactivity. And this is how websites are looking nowadays. And HTTP1 is finding it very, very difficult to meet these challenges. The challenges of delivering a large quantity of content, a large quantity of files to the browser in an efficient manner, and in a manner that makes the web experience palatable, makes the web experience worthwhile. So now, the average website downloads around 120 different resources. This is according to HTTP Archive. And in fact, over the last 5 years, the average size of the top 1,000 web pages has increased by over 300%. That's just in the last 5 years. So the protocol wasn't really designed to deliver this kind of content. It's really struggling. It's having a lot of problems actually getting the content to the people. And a lot of workarounds have been developed in order to compensate for the shortcomings of HTTP1. And if we're going to be looking at some of those workarounds, and then we're going to be looking at how HTTP solves those issues. So, how does a browser load a web page? Let's go back to basics. So how does a browser load a web page? The browser requests a web page from the server, finds that it requires more resources in order to render the page. It then starts to request these resources one at a time. So the browser will load style sheets number 1. It will wait for the server to respond with the resources. Then the browser will request a logo image, then it will request more resources from the server. And it is waiting for the server to respond. In the beginning, HTTP1 allowed only one request to be made via a single TCP connection. In HTTP1, this was addressed with pipelining. The browser was able to make multiple requests. So a request is sent for all of the required resources. A request is sent for the style sheet 1, then the style sheet 2, then the image, and then JavaScript. And the JavaScript resource is requested. And the browser waits for the server to respond with the requested resources. The server will respond in the order in which the resources were requested. So the browser must wait until the style sheet is returned if there are problems returning any of the other files. So this causes a blocking. Okay, so we're blocked waiting for resources to return. And this problem is called the head-of-line blocking. So instead of one connection, we have multiple connections. Okay? For example, on connection 1, the browser loads a style sheet. On connection 2, it loads JavaScript. On connection 3, it loads the image files, and so on. Now, this is how we get around the head-of-line blocking issue, by having multiple connections. So each one of these connections loads a different resource. The TCP sockets are expensive to create. This is the problem. TCP sockets are expensive to create. So every connection, you need to create a new socket. And for every connection, that's expensive. And this is not really a desirable situation to be in. And for each browser, there is a maximum number of connections. Now, given these restrictions, web developers looked for different ways to optimize web page loading. So, one way that web developers attempted to resolve this situation is CSS JavaScript file concatenation. Okay? So here we create one large CSS file containing all of the site's styles and one large JavaScript file with all of the required dynamic logic. Even the page itself could contain the required CSS and JavaScript. This will reduce the number of HTTP requests for a given web page. Okay, that's great. So we've reduced the number of requests. Not an ideal situation to be in, but we've reduced the number of TCP connections, so we've resolved, to some degree, the problem a bit. Additionally, another way is to use asset inlining. Inlining assets is a special case of file concatenation. It's the practice of embedding CSS style sheets and external JavaScript files directly into an HTTP page. For example, if you have web pages that look like this, you could run it through an inlining tool to get something like this. And as you can see, the CSS is now embedded directly in the HTML code. And so too is the JavaScript. Now we have reduced, again, the number of HTTP requests for a given page to just one. And we can continue. Additional optimizations include inline assets. Inlining assets or inlining images. An image is encoded, is base 64 encoded, and its code is inserted directly into a HTML page. So the way images are embedded is that the image is base 64 encoded and inserted directly into the web page. It is deployed to the web server with the image encoded inline, and then when the web page is loaded, the browser extracts it and decodes it using base 64. Now, that's great. That works well. You are reducing the number of images that you need to request, the number of TCP connections. However, the browser spends time decoding your image. So the processing power is being transferred to the browser. That's fine if your browser is fast, that computer is fast. However, caching becomes a problem. How do you cache images? Ideally, we'd want to do that, rather than load the browser with processing responsibilities. Additionally, image sprites. One image contains many smaller images. So here, all of the sprites are included in one single image. When the image is requested from the browser, JavaScript is used to cut each of the little sprites out of the main image, and they are used within the page. Now, this has to happen every single time you download an image. Every single time you have to process the image, you have to cut out your icons. It's, again, putting more processing power onto the browser. Fine if you've got a powerful browser, but again, still, it's just a workaround. So these are some examples of real-life image Google and Facebook. Okay, so another way we can overcome the maximum number of connections is to use domain sharding. Okay, the way this works is the way this works is that the browser can connect to different hosts and download different resources from different hosts. So here we have an example. We open a connection to server 1 and request the logo image and the icon image from server 1. Connection to a different server and request header and menu CSS. So we have opened 2 connections to 2 domains rather than 4 connections to 1 domain. Okay, this overcomes, again, the limitation on the number of connections, but you need a lot of domains. Okay. So what does our protocol say about sockets? Sockets are really what we're talking about here. So sockets are seen by HTTP 1.1 as a throwaway resource, okay? As the specification does not say very much about how they are to be used, nor is there any mention of how many sockets a browser should be open to a given host, okay? However, it's really just by industry consensus that a browser opens 5 or 8 or however many. In fact, Mozilla at the beginning opened just 1, and then Internet Explorer opened 4. There is no specification of exactly how many it must open, and browsers are just opening however many they see fit. So even though the specification says nothing about the number of open sockets, the browsers decided themselves to restrict it to an arbitrary number. So we have many sockets being opened in HTTP 1.1. In HTTP 2, it's a contrasting situation. Specification talks much about sockets. Sockets are seen by HTTP 2 as a scarce resource. Okay, the specification talks much about how they are to be used. And it implies that ideally, a browser should only open one socket to the server and do all it needs over this one socket. That's a great situation. You have one socket, you open one socket, you do everything through that socket. So the cost of setting it up is only felt once, And then once you have set up your connection, all of your communication goes nice and neatly through just one single pipe. That removes completely the need for domain sharding, and many of the other techniques that we've used before. So how does that actually work? Well, ultimately, what really are we talking about is that everything that was done in N sockets in HTTP 1 is now done in over just one connection. Okay? Everything is now done in just one connection. So let's move on to the top line features of HTTP 2. Okay, so what is HTTP 2? It is a new specification for the HTTP protocol. And it comprises of two specifications. It comprises of the main hypertext transfer protocol, version 2, RFC 7540, and HPACK, which is the header compression for HTTP 2, RFC 7541. That's very interesting. HPACK is something radically new, and I will be talking quite extensively about exactly what that is and how that manifests itself. It is a pretty detailed specification, so I'll be looking at the main points, just enough so that we can see how it optimizes our communication between browser and server. And it's worth mentioning that HTTP 2 is a binary protocol. It's based on frames. Frames I'll discuss and define a bit later, but frames are the basic unit of our communication, and is really at the heart of how we can get this response request multiplexing, which is really how we solve this, the major problems that we have in HTTP 1. And this the multiplexing multiplexing occurs over a single TCP connection, single TCP request and response connection, which is multiplexed and fully bidirectional. Okay, it's fully bidirectional. So binary frame TCP connection is broken down into frames. Okay, and we'll be looking at that in more detail later. And using header compression, we can remove duplication from header. We can remove duplicated header information. Okay, and in addition to that, we can also specify priority to give to streams, the streams that we use within our communications. And then on top of that, and this is the most exciting point, I think, for servlet developers, is server push. Okay, I'll be talking about this in detail later. I'll be talking about looking at some code examples and how this is really an exciting new part of HTTP 2 and as server developers, what we can do with this. And in fact, what we can do with this is still very unknown. And we'll discuss exactly why that is later. And then we need to talk very briefly about upgrading from HTTP 1 to HTTP 2. How do we communicate with the server? How do we tell them that we would now want to speak in HTTP 2? Okay, so request response multiplexing. Well, this is the most important feature. One of the most important features. I mean, this is my personal opinion. One of the most important features of HTTP 2 specification. Okay, as I said before, it is a multiplexed request response feature, which is fully bidirectional. Okay, you can communicate in both directions, and it works for both request and response. It's completely multiplexed. Okay, so let's have a look at some basic concepts. We need to define some concepts, some ideas that we're going to be talking about. So when I talk about a connection, I'm talking about a TCP socket. Okay. When I'm talking about a stream, what I want to talk about is a channel of communication through that TCP socket. Okay. It's a logical channel through that TCP socket. And through that, we have messages. Messages are logical. They're logical messages. So a request or a response and a control message. Okay, and we'll be looking in more detail about this later. And then frames. Frames are the smallest unit of communication in HTTP 2. And a request and response is broken down into smaller parts. Okay, it's broken down into smaller parts, and the smallest part is a frame. And there are different types of frames, which we'll be looking at in the next couple of slides. Each frame having its own responsibility. Okay, so all of this resolves the head of line blocking. Okay, these improvements resolve the head of line blocking, and give us the ability to communicate more effectively and efficiently in HTTP2. Okay, so the communication is broken down into frames, and those frames facilitate interweaving of logical streams. Okay, and we'll have a look at that in a couple of slides. So as a visual representation, this is what I'm talking about. So we have a connection, and for any given connection, you have multiple streams. Okay, for each stream, you have multiple messages, and for each message, you have multiple frames. Okay. You can see it's very hierarchical. And the frame, as you can see, is the fundamental unit of communication within HTTP2. So this is how we interweave our streams logically. I'm going to take a bit of time to explain this so we understand exactly what's going on. So the server does not have to wait for the complete communication before it does something else. This is how we resolve the head-of-line blocking. Okay, the server can respond continuously to these streams of information, not blocking on any one. Okay, so once you've taken, once broken down into frames, you can interleave them logically over a single TCP connection. So here, having a look at the diagram, you can see that stream 3 sends its headers first. Then later, it sends its data, which is its HTTP request body. And before the server receives the completed stream 3, it sends back response to stream 2. Okay? The server does not have to wait for the completed communication before it does something else. The head-of-line blocking problem does not occur. Okay, so you can see here, if we look a little closer, at stream 3, at the server end, it's got a frame type of headers. Looking further back, we've got stream 3 with frame type data. Okay, and I'll explain the importance of those frame types later in the next 2 or 3 slides. So let's decompose a particular frame. So what does a frame consist of? This is the basic unit of communication. Okay, so the frame has a header, and the header consists of some information. Okay, so the frame consists of a length of payload. It consists of a type. There are various different types. We've seen header, and we've seen data already. Some configuration flags, a reserve bit, and then stream identifier. Now, stream identifier is the number that you saw in the previous slide. It's the 1, the 2, the 3. It identifies a stream. Okay? And a particular communication has a stream number. And different frames will have the same stream number to identify that they belong to the same stream. Even though they are in disparate parts, even though they are in different frames and are sent in differently, separately, they belong to the same stream and are recomposed at the other end. Okay? So there are different types of frames. Right? There's quite a lot of types of frames. I'm not going to go through every single one. I'm just going to look at those that are particularly pertinent to our conversation of serverlets today. So header. The header type corresponds to the HTTP headers. So it corresponds to the method type, the file type, the path. It talks about the HTTP headers. And we can map headers from frames to headers in our traditional HTTP header. Okay, and we'll be doing that in the next couple of slides. Data, well, this literally corresponds to the payload. This is the data within our HTTP response or request. And you might have 1 or 2 or 3 or 4 or many frames of type data, depending on how much data you want to send. Priority frame, this is a frame where you can specify the priority of this stream. Okay. I'll talk a little bit about this later. I won't dwell on it too much. And then we have promise push. A promise push frame is used by the server push feature. This is used by the server to identify, to notify to a client that it wants to send some data. It wants to send some information. So it sends a server push promise, sends a push promise to a client, and the client receives this, and then we'll process it. And it might respond with an RTS stream frame type, which basically says, I don't want it. I don't want the information you're going to send me. I already have it in the cache. And we'll be looking at that a little bit further. So we can see here also we have other frame type settings, ping, go away, etc. OK, so let's have a look at how HTTP request is mapped to frames. Right, so mapping the HTTP request to a frame. This is a request. So on the left-hand side, we have an HTTP request, and on the right-hand side, we have it mapped into headers in a frame. Okay. So on the left, you can see this is a GET request for the index.html page. You can see that the host is example.com, and we specify the type as text HTML. Here on the right, you can see the equivalent header frame. Okay. So in the header frame, you have two configurations. The first is end stream, which is, in this case, set to true. It's set to true because the plus sign means true. This means that this is the last frame for this request. Okay, this is the last frame for this request. There are no other frames. In this particular instance, we only actually have one frame, one stream. Okay. And in this case, if you set the headers to true, actually it's set to false, it means there are more headers. Okay, there are more header frames. You can have more than one header frame. You can have more than one any frame. This configuration at the beginning determines if there's more frames to come of that particular type or not. So the first one determines, is this the last frame in the stream? And the second one determines, is this the last header in this section of types? So in this case, the type is header. So in this case, this is not the last header in our stream for this particular stream. There's another header, which I'm not showing here. So, I also want to say, also we map the familiar HTTP headers. The host is mapped to host, accept is mapped to accept. We can see quite intuitively what that means, okay, and how that is mapped. These are referred to in the specification as pseudo headers. They're not actually headers, they're pseudo headers, and they represent header information that we can see in this traditional HTTP request. Okay, so let's have a look at mapping the response to frames. So this is the response, and this is interesting because what we have here, we have two frames. The response is a response OK, and it's just sending back a simple text message. May the force be with you. And the header frame, mapping this to the header frame, and we can see, again, we have configurations at the top. It says here, end stream is set to false, which means this is not the last frame in this stream. But the header frame is set to true, which means this is the last header. And we can see we map our status, and we can map various other header information as well. And then we have a second frame. We have a data frame. This actually contains the data. This is a separate frame sent separately from the header frame. So the header frame is sent first, and then the data frame is sent second. And this is part of how you could interleave our responses to the browser. And here you see the type is set to data, and it does specify this as the end of stream. Okay. But we have a lot of duplication. So imagine in every single request, I make a request, the browser makes a request, I send some information in the headers to the server sends a response back to me, I send another request, etc., backwards and forwards, backwards and forwards. And there are lots of duplicated information, because in every single request, I have the method, which is going to be get or post. I have the schema, which is going to be HTTPS. That's not likely to change between requests. I have a host. Again, that's not likely, although it could change between requests. I have authority, I have accept, I have lots of headers that are the same for every single request and every single response. So we're duplicating a lot of information that actually we don't really need. So how does HTTP2 deal with this? Well, actually, it's HPACK. HPACK is our header compression. It compresses our headers. And it's quite simple. Okay? So mapping that to our first request, our header stream would be like this, okay? And what we do with this information is that the browser, what we do with this information is that the client and the server keeps a table of header information. It keeps a reference of header information. So we don't need to send it every time. So all we need to send is just the part that changes. It's just the delta. We're just sending the part that changes. And in this case, we're just going to be sending the path information. Okay, and we reference all the other headers back on the server or the client side. Okay, and then the server knows, server and the client knows exactly which headers we're actually using. And this saves, as you can imagine, quite a significant amount of bytes in sending. Okay, stream prioritization. HTTP2 provides the ability to attach priority information to streams, okay, which gives priority to one resource over another. Now, the priority can be entered either in the header frame or in the priority frame. And we have a hierarchy of frames. So we have also defined a hierarchy between streams. However, it is only advice to the server. It's only advice to the server. The server does not actually have to take any notice of it if it doesn't want to. It can completely ignore the priority information. And this is especially useful if it actually cannot respect the priority. If it cannot respect the priority for whatever reason, it will ignore it. Okay? So, let's have a look at Server Push. This is really exciting and something new in HTTP2. So what is Server Push? Well, Server Push eliminates the need for resource inlining. Okay, so before we saw how images were inlined, how we would use an inlining tool to put all our JavaScript and our CSS into our web page. We don't need to do that anymore. Okay, what we do is we use Server Push, and the way it works is like this. Okay, the client sends header frame. The client sends a header frame to the server to get a file. Okay, in this case, an HTML file, and at some point, the server will respond with a file. The server knows that if I am requesting that file, I will also want to request the resources that that file requires to render a proper HTML page. In this case, a CSS or a JPEG, or a JPEG and a CSS. So the server can proactively decide when it receives the request for the HTML page what resources that HTML page needs, because it knows that once that page is sent back, the browser is going to request all of the resources within that page, all of the image, all of the CSS, all of the JavaScript. It's going to request all of those. The server knows this. It's logical to suggest that that is what the browser is going to do. So what it does is it preempts the browser's request. And when the request from the browser comes in for the HTML page, it sends all of these resources, the CSS and the images and whatever other resources, back to the browser even before it sent back the index HTML page. So when the HTML page gets back to the browser, it already has the resources it needs. It doesn't need to go off and get those resources. Okay. However, the client, if it wants to, it can ignore those resources. If those resources currently exist in the browser's cache, it can ignore that request to receive those resources. So the way this works is that the server sends a promise push to the client saying, I want to send you a file. The browser goes, okay, I already have that file in my cache. I don't need it. And it sends back an RST stream to say, I don't want it, I'm rejecting it. Okay. Okay, so quickly, let's have a look at how to talk in HTTP2. Very simply, there are two ways. If you are using HTTP in clear text, you can use upgrade mechanism in HTTP 1.1. To send upgrade header to promote to a protocol called H2C. C means clear text, and then the server will respond in H2C. If you're using HTTPS, you can use the ALPN Application Layer Protocol Negotiation Extension, TLS. You send an extension during the handshake to the server side, and the server figures out that it is H2, and communicate continues in H2. However, Firefox and Chrome do not support H2C. So it looks like it's going to be HTTPS all the way. Okay. Okay, servlets are well positioned to enable HTTP optimization. They are the ideal abstraction over HTTP for this purpose. And this is because we don't really want to be programming frames at the servlet level. And the servlet push is the most visible improvement in the servlets. It creates the perception of improved performance. And of course, the server is best placed to know what resources it needs. Okay, it's best placed to know what logos, what images, what style sheets, what menu scripts. It's in the best position to know what the client needs. So that's where the server push is in the servlet layer. And that's why it's the best abstraction for that. Okay, I mean, it's not a replacement for WebSockets. It's a completely different paradigm. And frameworks are in a really good position to take advantage of this. JFS is in a particularly good position to utilize server push. And this is implemented in the push builder API in the JavaX package, JavaX servlet package. So let's have a very quick look at the journey. Okay, so a browser requests HTML index file. The server discovers that it needs some additional resources. We get an instance of the push builder from the HTTP request. We set the path to the file that we want, which is going to be the CSS file or the JavaScript file or whatever. We call push, that pushes it. We reuse our instance and set a JavaScript file and push that. And then we finally respond with the HTML file. So this is what the API looks like. It's in the JavaX Servlet HTTP push builder package, and you get an instance simply by calling get push builder on a HTTP request object. So when it's constructed, it's automatically constructed with some defaults, and the only thing you really need to set is the path. Okay, that's the only thing you really need to care about. And here you can see there is an example of how to obtain this and to push, in this case, a logo image. So this is an example, a very simple example of how it might be used in a servlet. Okay, here we are using a request to determine what the page is. We are testing to see if a server push is supported, and then we are pushing our resource. Okay. A slightly more sophisticated implementation of this is to use it as a filter. Okay, this filter will intercept any HTTP request to the server. It will analyze the page. It will determine what resources are in the page, and it will push those to the client before it even gets to our servlet. Okay, and in actual fact, this is how Jetty has implemented the push servlet, the push server. They actually have a push cache filter, which is far more sophisticated than this very simple example, and takes care of that all for you. So you don't even need to do this. Okay, this is already built into Jetty's servlet package. So frameworks. Frameworks are a good case. This is something that's still currently in development and is just an idea that was mooted by some tech leads at Oracle. And when you're rendering a JSF page, you're likely to be calling the encode resource URL, and this is a good place for the framework to take care of creating a push builder and pushing out our resources. So Java 9 also supports server push. It's in JEP 110. They haven't reinvented the HTTP client. It's pretty much the same as it was before. They've just extended it, so it supports both HTTP 1.1 and HTTP 2. The way it works is that you get an HTTP client builder. From that, you get yourself an HTTP client. Then you get yourself a HTTP request builder. And from that, you build up your HTTP request, post, and get. Okay, so this fully supports server push, and there are two modes, blocking and non-blocking. The non-blocking mode, you can use executive service and computable features. So here's an example of how you would do this. You get a HTTP request, you call the get, you call the create, you pass it a URI, add your headers, add your get, and do your response. You can also get from this your response status code and response body. And if this is the post, similarly, you can set your body using from string method here. Okay, so as I mentioned before, browsers can disenable or enable a server push right at the very beginning by sending out settings enable push. And also they can reject each push promise by responding with an RST stream frame type. So who supports it? Glassfish currently is a reference implementation, but there's not much going on there. Pyara have just created a branch in JEE for their development. Now, Jetty is really interesting. They've really pushed the boat out and have implemented their own version of the push builder and the push cache filter. This is a very interesting implementation and it's certainly worth a look. Wildfly, you can use Undertow. That currently supports server push. Tomcat 9 also supports it in the JavaX servlets or HTTP packet. And Netty also has an interesting, also takes advantage of many of the headline features of HTTP2. This is a very simple configuration. You need to configure TLS. This is a simple example of how Tomcat might configure TLS. So what about SPDY? Well, SPDY, its original objective was to focus on reducing the web page loading time, and it was successful in doing that. And it was actually the forerunner for the HTTP spec. HTTP2 spec was based upon SPDY, and it formed the first draft. However, it was really only just a stepping stone to get to where we are now, and support from SPDY has been dropped by Chrome, or will be dropped by Chrome in favor of HTTP2. So performance, there are a number of tools on the internet that you can visit that will allow you to demonstrate the performance of HTTP2. Here's an example that I did a couple of days on Cloudflare. They have a really neat tool that shows that HTTP2 gives you 4 times faster performance. So visit those sites and have a play for yourself, and you'll see exactly how beneficial HTTP2 really is. Tracking adoption, well, okay, servers advise HTTP2 support during SSL handshake, and by using Shodan.io, you can search for that information and build up some interesting stats. Now, what I've discovered is that over the last few months, between December and April, adoption of HTTP2 is up 10%. However, this growth really has actually come just from the incumbent versions of HTTP2, like Draft 17, Draft 14. Server providers are changing from those versions to HTTP2, and in actual fact, there's been no net increase in HTTP2 support on the server side. But we'll see how that grows. Okay, very little time for questions and answers. Probably about 2 minutes. Anybody got any questions? Anybody got any answers? Oh, yes.
Thank you for the great information that you provided. My name is Alexei, and I have a question. That's a question about layers. And for instance, in HTTP approaches, all resources are defined on the HTML level. So on the top of headers, I have to define my styles, JavaScript, and so on. But using this approach, it looks like I have to define it directly in Servlet on Java level. Is it correct, or?
If I'm understanding your question correctly, web developers don't have to do anything. The browser takes care of it all for you. Okay? So web developers don't actually have to do anything. It's the server side that actually will make the change. Because browsers are actually doing all of the work for you. They're managing all the headers. You don't need to change your HTML code. You don't need to change anything on the front end. Okay? Absolutely nothing. It's the browser that does all of this hard work for you. You might want to remove all of your inlining of assets and all this kind of stuff, but it's not necessary. You don't need to. In order to take advantage of server push, for example, as a web developer, the front end, you don't need to do anything at all. Okay? It's the server side. And if you use Jetty, for example, you don't even need to do anything because they have this wonderful servlet push cache filter that analyzes the files for you and does it all for you. JSF, again, also will do a lot of the work for you as well. So really, unless you're really going deep into this and you really are looking at something right in the heart of it, there's not a lot you really need to do. You just need to know about it and what it actually does. So from the front end, you don't need to do anything.
Thank you. And my last question, I would like to ask you about browser supporting of these technologies. Do you have any table, or where can I take a look?
I didn't include in my presentation a table of browsers that support that. that might be a good idea for the next time I do this presentation. But yeah, no, I think if you do a quick search on the internet, you ought to be able to find something. I can't point to something at the moment off the top of my head, but certainly all the latest versions of browsers that are important to us support this.
Okay. Thank you very much.
Thank you. And also, it's probably also worth mentioning that it's going to have to be HTTPS. Chrome and Firefox don't support clear text. So now everybody is going to be having to communicate in HTTPS all the way. There's a question there? Blank page means no time left. Okay.
Hello.
Yes.
Thanks. My name is Pavel. I would like to basically ask, HTTP 1 was really simple to follow. You
Yes.
have like one response and then one
Yes.
request and then response. And what about HTTP 2? Because you have the frames that are being sent. Is it hard to, for example, debug if there is problem, or how error handling is made in HTTP 2?
Well, yeah, no, that's a very good point. It is much more common. I mean, HTTP 1 was wonderfully simple and relatively easy to get to grips with. HTTP 2 is far more complicated. And exactly how we're going to be dealing with that is, will depend on those who like to develop tools. There's no doubt there will be plenty of people who will be developing very neat tools that will allow us to debug and monitor HTTP 2 communication. But yes, HTTP 2 is far, far, far more complicated. It needs to be in order to give us the kind of web browsing experience that we're now accustomed to. We like dynamic pages, we like complicated websites with lots of graphics, and we want it fast. We want it now. Okay. I mean, 100 milliseconds is a long time in browser world. Okay, I'm going to be around all day. Is there any more time for questions? No. Okay, I'm going to be around all day, so grab me and have a chat. Let me know what you think, and have a nice conference. Thank you, everyone, for turning up. And before I go, I might want to mention that I have another speech, if you haven't had enough of my voice already, tomorrow in the morning about Java EE and design patterns, how Java Enterprise Edition has changed the way we implement traditional design patterns. Okay? Hope to see you all there.